Hi, and welcome to Chapter 3, the normal distribution. Now, even though the normal distribution is going to be the most important thing in this chapter, it actually has a lot more. So let's just start from the beginning. In the previous chapters, we had looked at histograms, taking data and turning them into graphs, and thinking about numbers that involve them. Now, sometimes, as we saw before, data follows a specific shape. We're going to give those shapes names today. If there was a shape we understood, we could use curves to approximate the data. And this is especially useful if the data we collect is only part of the group we care about, because then we would have maybe imagined that the group as a whole might not exactly fit this data anyway. And so these curves are theoretical. They're not exactly matching the data, but we're imagining that they exactly match some theoretical data out there. We call these imaginary curves density curves, and there's a couple things we know about them. First of all, when we draw them, they're always on or above the x-axis. The total area under the curve is 100%, or as a decimal, 1. And the area under the curve between any two values gives the proportion of observations between those values. Now again, this is a theoretical group, but we could imagine observations from this theoretical group. So I'm going to talk about each of these three rules, but I'm going to give us a really quick little example to give them context. Suppose I collected data on height of people or whatever. And let's imagine that these bars are actual data, and we could imagine this curve that might represent some imaginary data. Well, first, let's check those three rules with the actual data and see why those rules exist. Rule number 1 was always on or above the x-axis. If I wanted to say, make a bar below the x-axis, what exactly would that even mean? Like, the height of the bar is what percent in this case of our imaginary data would fall in that group. And bar that goes down would have a negative percent, maybe? I don't know. So bars always have positive heights, and therefore our graph should always be above the x-axis or on the x-axis. Example here where there's 0 height. Number 2, the total area under the curve is 100%, or 1. Well, if you think about it, if 10% of our data is in the first block, 20% is in the third block, well, we put all of our data in this graph, right? 100% of our data. So when we draw a histogram, if we're graphing it using percents, that total should always be 100%. It just means you have all the data. And so that's why that has to be 100%. And now for the last one, the area between two values under the curve is the proportion or percent of observations between those values. So let's say we said 62 to 66. Well, that's 20 and 40. Aren't we looking at all this area to find that percent? So it turns out that when you change from bars to a curve, those things still want to be true. The area in between still measures what percent is in that group. The total percent still needs to be 100, and dipping below the x-axis would never make any sense. So, some real quick notation. If we remember from Chapter 2, when we collect data and, say, put it into our calculator, we calculate the mean of our data and we call it x bar. We sometimes call this the sample mean, the sample being the stuff we took data from. We'll define that officially later. And the standard deviation was called S. And again, sometimes we call this the sample standard deviation. Those names won't have much meaning for us yet, but in case you look back at these notes for, say, the midterm and the final where you have more knowledge, that'll be helpful. But now we're going to use different notation. when we're talking about a theoretical density curve, not something where we collected data, but something where we're imagining this data we don't actually know about, the mean is going to be this symbol, and this, we pronounce it mu. It is the Greek letter m, lowercase m, mu. It's like a U with a long tail in the front. And the standard deviation is what we call sigma. It is the Greek letter S, and it's a circle with a little hat. Okay, so please, 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 if it's from data, the mean is x bar, and the standard deviation is S. If it is from a theoretical distribution that we don't really know about, the mean is mu, and the standard deviation is sigma. Theoretical is Greek letters, almost completely. Data is regular letters, American, English, whatever. So, this is going to be very, very, very important to know the difference. So keep that in your mind. So, how do the mean and the median compare to each other on a density curve? And the short version is really just like they did in data. So for a symmetric density curve, both the mean and the median happen to be right there in the middle, and they are equal to each other. But if our data is skewed, then the mean is going to be pulled down the tail just like it was pulled down the tail in data. So if we have something shaped like this, I'm not going to make you pinpoint exactly where mu or the median are, the mean or the median, but I might make some tick marks and say, okay, which one is the mean, which one's the median? And you'll know the median is more toward the center and the mean is more toward the tail. Now, what they actually represent, if you wanted to measure them, where would you put them? The median, by definition of how we may find it, cuts the area in half. It cuts the lowest 50% of the data from the highest 50% of the data. So if we were to cut a line and this area was half and this area was half, that line that we cut would be the median. Now the mean, we have to think a little more three-dimensionally. If we were to make this shape out of, say, cardboard or something, and we would try to balance that shape on our finger, if we didn't put it in the right place, it'd tip and fall over, right? The mean, mu, is the balance point, where you would need to hold it on your finger in order for both sides to balance. And if you're not comfortable with these ideas being different, go to a park with a small child, sit on a teeter-totter. The bigger person sits closer to the center, and the little person sits farther out, and then they will balance. So, there are two common density curves that we're going to talk about in this class. The first one is called uniform, and the notation for that is a big U for uniform, and then square brackets A comma B. And what that means, the uniform distributions takes all values between A and B and no values outside. So when you say U parentheses A comma B, you're saying these are the numbers we're allowed to use. Now, be careful. This includes all numbers, fractions, decimals. If I say 0 to 5, I don't mean 0, 1, 2, 3, 4, 5. I mean 0, 3.7, pi, 8/3. Yeah, that's between 0 and 5. So be really, really careful here. A common mistake is think of just whole numbers. You want all numbers between those two values. Now, what makes this uniform, if you think of the word uniform, well, I think of like those outfits people wear to work that all look the same. Uniform means all the same, and so all outcomes are equally likely. And what that means is when we draw it, the height of our line we draw, our curve, it's not very curvy in this case, is a straight flat line. Now, sometimes people, just to give it a little extra definition, draw the lines where A and B are to be like, okay, that's the starting and that's the stopping. They're optional lines, but it does turn our shape into a nice little rectangle. And that fact that it's a rectangle is going to become very important in solving problems with them. So feel free to add those lines if you like. They are optional. So let's do an example with a uniform distribution. Suppose the amount of time you wait for a bus is uniformly distributed between 0 minutes and 20 minutes. So you show up, it could be there waiting for you, you don't have to wait at all. You could wait 20 minutes, you could wait anywhere in between, and all those times are equally likely. Part A, draw the density curve, include the value for height of the curve. So, density curves, start on a graph, and our values are from 0 to 20. So if we wanted to write it notationally, we'd have uniform from 0 to 20. So I'm going to put the values on the x-axis, 0 to 20. And I know that the height is constant for the whole time, and I like to put that little line there. So that is a picture of our distribution, our density curve, but it specifically asks us to find the height. We generally always want to find the height anyway. Now, we didn't get told anything about the height. All we know is that it's a constant height, and that made a rectangle. But we do know that the total area under the curve has to equal 1 or 100%. That is true of all density curves. And the nice thing about this is because this is a rectangle, we know the area of a rectangle is base times height, or length times width, however you want to call it. So we can look at this and say, okay, what is the width here, the base? Well, it goes from 0 to 20. That is a gap of 20. Please note it's not just the ending point. If I said 5 to 20, that'd be a gap of 15. So always subtract your endpoints. So using this, I can go to my formula and say, well, the area has to be 1. My base is 20. What does my height have to be? And with a little bit of algebra, we can see that our height is 1 over 20. The height is always the reciprocal of the base, if you know what that word means. And we can either write 1 over 20 here, or if you prefer decimals, 0.05. And that's our density curve. It's just a rectangle, and you find the height using the endpoints. So part B says, okay, how often do you have to wait more than 15 minutes for the bus? So what I'm going to do, I'm going to redraw this picture really quick. 20, 0, 1/20. 15 is roughly here. And so what I want is more than 15. More than 15 is 15 to 20. That's what I want. And because proportions or percents come from areas, all I have to do is find the area of that shape. And area of a rectangle, because that's still a rectangle, that blue area, is base times height. In this case, my base, 15 to 20, is a length of 5. So 5 times 1/20 is 5/20, or 1/4, or if you prefer, 25%, 0.25. So how often do you have to wait more than 15 minutes? 25% of the time you have to wait more than 15 minutes. That is not the only way you could find the area of this. There are other ways, but that's just the most straightforward way. Well, straightforward's an opinion, but it follows area formulas, and then you don't have to take any other strategies. So for C, how often do you have to wait less than 2 minutes? Well, let's do basically the same thing. We're going to draw a real quick version of our picture. But now we're looking for 2, and 2 is somewhere over here. It doesn't matter where we put it because we are just using this to get an idea. We're using the picture to help us find the math. So our base is 2. And so our area is 2 times 1/20, which is 2/20 or 1/10 or 10% of the time. Okay, now real quickly, what if I changed the last question? Instead of saying less than 2 minutes, I said 2 minutes or less. Part C is like x is less than 2. Part D is saying x is less than 2 or equal to 2, 2 or less. What's the difference in the answers for these questions? Notice it's not like we made a list, 0, 1, and 2, now I'm going to leave off 2. How do you make this rectangle but leave off the 2? And it turns out that the answer doesn't change. When we include that endpoint or we don't include that endpoint, it has absolutely zero effect on our answer. Because on density curves, the probability of getting any one specific value is 0. So less than or equal to have the same answer. So let's think about how that works. How does that idea match the definition for how to find the proportion of observations between values? Now, couldn't we say that x less than or equal to 2 really could be broken down to x is less than 2 plus x is equal to 2, right? Okay. If we were to use areas to find x equal 2, let's draw a quick picture. Zoom, 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 20, 1/20, 0. Here's 2. Now, we don't want to shade the less than side. We don't want to shade the greater than side. We just want that exact place. The area, well, the height is 1/20, but the width, there's no 2 points. We don't start at somewhere and end at somewhere else. We started at 2 and ended at 2. The width is 0, and therefore, the area is 0. And one single value doesn't matter. Another way to think about that, if there are 6 different options and they're all equally likely, each one happens 1/6 of the time. If there's 1,000,000 different options and they're all equally likely, each one happens 1 out of 1,000,000 times. Because this is every value between A and B, or between 0 and 20 in this case, there are infinitely many numbers between A and B. And so 1 divided by infinity, well, as the number you divide by gets bigger, your answer gets smaller and it heads towards 0. So just a little bit of expanded idea there. You don't have to get that if you don't want to. So that's all we're going to say about uniforms. Know they're a rectangle, know how to find the height, and know how to answer questions with them. The rest of the day, we're going to talk about the normal distribution. Yes, the thing the chapter is named after. And just like a uniform was uniform A comma B, the normal distribution is n, parentheses, mu comma sigma. We already talked about mu and sigma, right? Mean and standard deviation. So they're not square brackets because this isn't really an interval anymore. We're just saying, hey, I have a normal and it has a mean and it has a standard deviation. That parentheses is just saying, hey, think about this. Now, normal distributions actually include an entire family of curves called normal. They all look the same. They all look kind of like a mountain, and they all have similar properties. But what makes each normal distribution unique is where its center is, mu, which also, it's the mean, but it's also the median because it's symmetric, as we'll talk about in a second. So the mean is the center. The spread, or standard deviation, those two things determine what our specific normal distribution looks like. So to determine which normal distribution we're using, we need to state these. We need to say my distribution is normal with this mean and this standard deviation, and that is why this is the notation. When we write normal parentheses 5, 2, you're like, oh, that's the normal distribution that has mean 5 and standard deviation 2. So that's all we need to know which normal we're talking about. Now, mean is the middle. That's kind of easy to see. It's the top of the mountain. But let's talk just briefly about how we measure spread. What does that standard deviation mean? And it's really not going to be important, but just so you know. If we start at the top of the hill and we go down, at first the hill is flat and it gets steeper and steeper and steeper and steeper and steeper. And then at some point, it starts getting flatter and flatter and flatter and flatter. This point where it goes from steeper to flatter, that is one standard deviation away horizontally from the middle. So where that change happens at mu plus sigma and mu minus sigma. For those of you who've taken calculus, that's called the point of inflection, where the concavity changes. None of that is important to us. The only time this idea is even going to come into play is maybe on homework it'll say something about this idea. But this idea, it's important to the idea of what a normal represents. It's not going to be something we use. So other properties of all normal distributions. They are perfectly symmetric. The left side is an identical copy of the right side, just flipped over. The peak is at the center. They take all values. This picture didn't go on forever, but this picture isn't a perfect drawing anyway. So they actually take all values, negative infinity to infinity. The ends don't happen hardly ever at all, almost zero, but technically they're still possible. And number 3, when values are measured in terms of sigma, the standard deviations, then areas between values are the same for all normal distributions. And one way we see this fact is in what they call the 68, 95, 99.7 rule. So let's look deeper into that, and that's going to help you understand what number 3 meant. About 68% of all observations, again theoretical observations, fall within one standard deviation of the mean. Now from now on I'm just going to write 1 sigma of mu because standard deviation is too long of a word. So if we start at the mean and we go out 1 standard deviation either direction, like we did in this picture, then 68% of our observations about will fall in that group. Now, about 95 of our observations fall within 2 standard deviations of the mean. So if we start at the mean and add 2 standard deviations or subtract 2 standard deviations, in that group is 95% of our observations. And if we go out 3 standard deviations from the mean, we're going to collect about 99.7% of our observations. Now, just really quickly, the reason it says about is not because the answers change for different normal distributions. It's because the actual answers are not beautiful, nice round numbers like 68%. 68.269% would be closer to the exact answer for within 1 standard deviation of the mean. But that's not as nice to use. So we just rounded the answers, and that's why we say about. Now, really quick note. We will learn how to find more exact answers like that 68.2689% in a little bit, but we need to be really careful to check our directions. On our homework, quizzes, tests, if they say use the 68, 95, 99.7 rule, then don't do the more exact method that we haven't learned yet. You have to use this 68, 95, 99.7 rule. But if you're not told to use the 68, 95, 99.7 rule, then they want you to use the exact method. Do not use the 68, 95, 99.7 rule unless you're told to. So this rule actually gives us a lot more information than we might imagine. So let's just look at an example. Not specifically an example, but here is a normal distribution with the mean mu, and I went up 1 standard deviation to mu plus sigma, and I went down 1 standard deviation to mu minus sigma. And these are in the wrong places, it's just pretend. And this rule tells us that 68% of our data is in that space that I'm going to now shade green. Okay, but what do we know about that? Well, since this picture is symmetric, this middle chunk is also symmetric, so this half of the 68% is going to be, so this half of our picture is going to be half of the 68%, or 34%. But we also know that the entire right half of the graph, since mu is not only the mean, it's also the median, we know that 50% of the data is on this side. If 34% of it is already in the blue area, then the yellow area has to be the 50% minus the 34%, which is 16%. But since it's symmetric, that means that this little piece as well is also 16%. And this piece here is 34%. So we broke up our picture into 4 different pieces. Now, if I were to add mu plus another sigma, so we jumped up 1 sigma, we're going to jump up another sigma. I know that the total area, let's do mu minus 2 sigmas as well. I know the total area is about 95%. Well, that means the parts, the 2 sides we're not including is the leftover 5. Half of that leftover 5 is 2.5%, and the other half is 2.5%. So this middle is 95, that leaves 5 for the outsides, and it gets broken in half. Okay, now, technically this yellow goes on forever. So now we can say, oh, this part right here that's just between 1 standard deviation and 2 standard deviations away, well, that's 16 minus 2.5. Now I'm going to stop. I'm not going to find that. I'm not going to go deeper. But notice, if we wrote mu plus 1 sigma plus 2 sigma plus 3 sigma, mu minus 1 sigma minus 2 sigma minus 3 sigma, we could break this up into lots of tiny little parts, and we could find the area in each of those groups and combine them however we wanted. So this is actually a whole lot of useful information. So let's use that and find some examples. Suppose the height of adults 20 to 25 years old is normally distributed with mean 67 inches and standard deviation 3 inches. Use the 68, 95, 99.7 rule to find the following. What percent of adults are between 70 and 76 inches tall? So realistically, when I see that word normally distributed, the first thing I want to do is draw a hill, the normal distribution. And I always like to put in the mean. Now, some people want to put in the standard deviations, but they're not particularly helpful unless we're doing the 68, 95, 99.7 rule, and that they're only helpful so far as they match our points. So I'm just going to put in our points. 70 is somewhere to the right of 67, and 76 is even past that. What I want is this area. So let's think about how that is related to our standard deviations. 67 to 70, that's a jump of 3, or 1 sigma, 1 standard deviation. Now, 70 to 76, that's a jump of 6 or 2 standard deviations. So when we look at this, we could say, oh, this is 1 sigma, 2, 3 sigmas. Yes, my picture is not to scale. We don't care. It's just to help us visualize. So what we're going to do is we're going to say, I need to find this shape using all the other stuff I know. So, okay, let's start with, we're going to cut it into pieces. We can combine shapes or we can cut away shapes. Notice this piece I want is almost an entire right side. It just doesn't want this little piece. So what we want, the blue piece, is like the whole right red chunk minus the green chunk. So what we're going to do is we're going to find the area of the red chunk. Okay. Since the 70 is 1 standard deviation above the mean, we know that from this number, which isn't important, but let's write it down anyway, 3 is 64. That's 1 standard deviation below 67. So, since this is 1 standard deviation up and 1 standard deviation down, we know that's 68% of our data. Well, that means the 2 tails left over are what's ever left from 100%, or in this case, 32%. Well, that's for both sides. So one side is going to be half of 32%, which is 16%. I found the inside using the 68.99.599.7 rule. I then figured out where the 2 tails were and took half of it to get 1 tail. We found the same value a different way before by saying if 68% is in the middle, then half of that is 34. Subtract that from the total 50% on the right. It doesn't matter which way you get it. There's lots of good ways to get it. So now we're going to find our little green area. And our green, our 76, the line that breaks up the green from the blue, is 3 standard deviations. So if we went out 3 standard deviations either way, that would be 99.7% of our data. That means the tails, well, both tails are going to give us the leftovers from 99.7%, which is 0.3%. So one tail is going to give us half of 0.3%, which is 0.15%. And therefore, our blue area, which is what we wanted, is the 16% of all the red minus the 0.15% of the green, which is 15.85%. That is our blue area. So what percent of adults are between 70 and 76 inches tall? 15.85% of them. And again, this data is all made up. So let's do that one more time so we can get a feel for that. What percent of adults aged 20 to 25 are between 60 and 67 inches? So again, I'm going to start with my picture. The mean is 67. And I want between 61 is somewhere over here, and 67. I want this. Now, it's going to be the same ideas we just did before, but this one's actually a little nicer because this one is the red piece minus the green piece, just like this one was the red piece minus the green piece. But the difference being, since our red piece by coincidence uses the mean, our red piece we know, is 50%. That's the area because it's half of the picture. And now we just have to find the green area. So let's remember, 61 to 67, that's a total of 6, or in this case, 2 standard deviations. Well, 2 standard deviations either direction would be 95%. Oh, we didn't even have to do that part. So let's finish what we did, and then I'll show you another way to do this. So that means the outsides together are the rest of that 100% or 5%, and each of these is 2.5%. And 50% minus 2.5% equals 47.5%. But an easier way to do this, had we just seen it right off, because there's lots of ways. If we know the middle is 95%, what we want is half the middle. Again, only because one of our endpoints was the mean. So we could have done, okay, 95% is from mu minus 2 sigma to mu plus 2 sigma. I wanted half of that, just minus 2 sigma to the middle. And either way, you get the same answer. So there's lots of ways to do a problem. It just depends on which way you see, which way works for you, and you mix and you match. You can add things together, you can subtract things, get creative. Now let's go a different direction with this. How tall are the tallest 16% of adults? 20 to 25 years old. So again, we're still in the normal. Our mean is still 67. Now, here's where we have to be careful. We're looking for tall people. Tall people have big numbers, and so they're going to be somewhere over here. And we want this area to be 16%. And what we're looking for is this number. So let's just do some experimenting really quick. If that tail is 16%, then this tail would also have to be 16% because they would match. They don't look like they're matching because I did a horrible picture drawing this. And when I do that, I'm assuming that I went out the same number of sigmas in either direction. I just don't know how many sigmas it is. 1, 2, 3, 4. So the blue area is currently 16 plus 16 is 32%. That means that the inside is 100 minus 32, or 68%. Ooh, that's a number I recognize. 68% of my data is within 1 sigma of the mean, and that means that this number of sigmas we went either direction was 1 sigma. And so this number is 67 plus 1 sigma, which in this case is 3, or 70. So I used the symmetry to find the area of both tails. I used that to find the area of the middle, and that should be either 68, 95, or 99.7 because those are the only ones we know. You will never be asked something with a middle chunk. It'll always be one of the ends. Now let's talk about how we answer this because this is really important and people get this wrong. How tall are the tallest 16% of adults 20 to 25 years old? Are all the tallest adults exactly 70 inches tall? No, they're not. The answer is 70 inches or taller, right? This is 70. I wanted 70 and bigger. So when it says how tall are the tallest or how tall are the shortest, it's going to be this or more, this or less. Notice you didn't have to give me a different side. You didn't have to say 70 to 80. You just said 70 or more. So let's do one more. How tall are the shortest? 2.5%. So we draw, the mean is 67. Now this time short people have low heights, and I know this area is supposed to be 2.5%. Well, that means this other area is 2.5 as well, and that means together the two blue areas are 5%. That means the middle is what's left over from 100, or 95%, and that goes with 2 standard deviations. So our answer is 60, oops, careful, I wanted the short people. This is the number I was trying to find. So my answer is 67 minus 2 standard deviations, or 2 times 3, or 61. And that means my final answer is 61 inches or shorter, because I want short people. Okay, just a really quick note. Not all things shaped like a hill are normal. We will run into things later in the term that are not normal, that are shaped like a hill. So just be aware that they have to have these things be true, 68, 95, 99.7 rule, in order for them to actually fit in the normal distribution. We're not going to take that in mind when we draw it. We're just going to draw a hill, but technically. So let's now talk about these other methods that are more exact and less restrictive. Notice if I asked you the tallest 5% of people, well, one side being 5%, the other side being 5%, that'd be the outside was 10, the inside was 90. That didn't fit any of my 68, 95, 99.7 rule numbers, and so I couldn't find it that way. So there's 2 ways we can use this more useful method, more exact method. We can either be asked to find the area under the curve, be asked to find the proportion or the percent of observations, or we can be given the area under the curve, the percent or the proportion, and asked to find that cutoff value, that line that cuts off that percent. So here's a picture of each. I could say, find the proportion of observations between A and B. And on the calculator, there is a lovely little formula for this. It's called the normal CDF button. That's normal for normal distribution. And CDF stands for cumulative distribution function. Cumulative meaning everything all added together from A to B. And when you use that, your calculator wants you to give it the low value to start at, the high value to end at of your group you want to know about, and then it needs your mean and your standard deviation to know which normal you're talking about. And once you give it that, it's just going to give you the area in one quick swoop, no work. Part B, I'm going to give you an area, and I'm asking you to find this one value that cuts it off. And on the calculator, that is called inv norm. Inv is short for inverse. It's the mathematical way to say opposite or backwards. And normal again for normal. And for this one, it's always going to want the left area in decimal form, not percent. And then again, it needs mu and sigma to know which normal we're talking about. And once it knows this area, that's all it needs to find this value. So we can do this using a table, or we can use this using our calculator like I just showed you. It'd be nice that you know how to do both. The calculator is very useful and convenient, but notice there's no calculators allowed on quizzes or tests, so being able to do this by hand is also very important. If we do not have a calculator, we're going to have to use what's called Table A in our book, and that is on pages 698 and 699. But that table only works for one specific normal distribution, and that is called the standard normal distribution, and you should know what the standard normal distribution is. The standard distribution is so important that we give it a special letter Z, and it is normal with a mean of 0 and a standard deviation of 1. So if our data isn't standard normal, we're going to need to convert our data into standard normal, and the way to do that is with this standardizing equation. This x is some important value we want to know about. We subtract off the mean of our original data, or not necessarily data, theoretical distribution. We divide by the standard deviation of our theoretical distribution, and that gives us the standard normal version of our other normal problem. One interpretation of the Z is how many standard deviations our number is from the mean. So a Z of 3 says, oh, our number was 3 standard deviations above the mean. A Z of negative 1.5 says our number was 1.5 standard deviations below the mean. And this can be useful in comparing two values with different means. Okay, so instead of starting a problem with this, I have a feeling this video is already super long, so I'm going to stop now, call this part 1, and in part 2 I will show you how to actually solve these normal problems both on your calculator and in your book. If you have any questions, feel free to let me know. Have a good day.